Hi everybody, welcome back. Today we're talking about lesson 20. These are trigonometric equations. Those are equations that have trig functions in them. Sines, cosines, and tangents, maybe secants, cosecants, and cotangents. And the way the lesson is broken out is first we deal with very basic equations. That doesn't mean that they're easy necessarily, but they're very simple looking. They just look like a trig function equal a number. And we're going to start by looking at equations like this. Tangent of x equals some number c. When we have an equation like this, how do we find the correct angle x to solve that equation? And in particular, if there's more than one answer, then how do we make sure that we've found all the answers? So that's the idea. Let's start with tangent x. Here we go. This is example 20.1. Solve for x. Tangent x is equal to radical 3. That's our equation. Now, you'll notice that the unknown, the x, it's inside the tangent function, so it's like an angle. And this is like asking what angle x has tangent equal to radical 3. And the fact of the matter is one of those angles, x, we can find just by knowing our trig functions at basic angles. So let's see. Here's our table of trig functions at basic angles in the first quadrant. And here we're looking when tangent x is equal to radical 3. And you'll see that the angle that comes from is the angle pi over 3, or 60 degrees. I'm going to use radians here, so let's say pi over 3 for that angle. So one solution is x equal pi over 3. All right, here is the trouble. That is not the only solution. And in general, when you think about tangent of an angle, as the angle increases, if you can picture in your head that unit circle, the angle keeps increasing and eventually it goes all the way around the unit circle back where it started again. And then it goes around the unit circle again. And so if you found an angle where the tangent was equal to radical 3, and then you went all the way around from that point, a full circle around back to the same place, you would have a new angle that still pointed to the same place, that still had a tangent of radical 3. So we need to take that into account. And in order to explore this more deeply, in this case, let's go ahead and look at a graph. So we're going to consider the graph of the tangent function. Here is my tangent function in purple. As we know, it consists of this repeating pattern, these sort of almost vertical diagonal stripes shown in purple with a vertical asymptotes in between each one. And the solution that we found, so what we're looking for is when is the tangent, so the angles appear along the x-axis here, and the values of the y-axis are what the tangent is equal to. And so this is when is the tangent equal to radical 3. Now, radical 3, you can see maybe on the left, it appears there, radical 3 is equal to 1.73 something. So it's between 1 and 2, somewhere right in here, 1.7. That's the value of tangent we want. And if we go over, we see that right here, that lines up with this value of x, and this value of x is pi over 3. Now, we can see that more clearly if we turn on, this is going to give us the horizontal line, y equal radical 3. And what we're really asking is when does the tangent function have a y value that hits this orange line, the radical 3 line? When is tangent equal to radical 3? And one of the places is right here. Let's see if I can just activate that grid point. And you'll see it gives us the coordinates. The x is pi over 3, and the y is 1.732. That is a decimal approximation of radical 3. So one of the places where the tangent of x is equal to radical 3 is when x is equal to pi over 3. That's right here, a little below pi over 2. Okay, so we found this x value is one solution to this. But of course, just by inspecting the graph here, the tangent function, which is all of the purple pieces, it runs into that horizontal line of radical 3 more places. So if we move along, there are other places where the tangent gives you an answer of radical 3. For example, right over here gives you an answer of radical 3. And the x value of that is down below. We need to sort of think through where that x value is. Okay, here's how we're going to do it. you may remember that the tangent function is what we call a periodic function. Periodic just means it repeats. And so it's this pattern here, that upward curved diagonal pattern that repeats over and over again. And the period of this function is exactly pi. So from the center right here where it crosses the x-axis to the next place it crosses the x-axis is pi. And then pi again, and then pi again, and it goes both in the positive and negative directions. And that's true starting at 0, but it's also true starting at another point on the graph here at pi over 3. If we move up to the next place where it attains the same value, that distance is going to be pi. And so we can find this x-coordinate by taking this x-coordinate, pi over 3, and adding pi to it. So this is pi plus pi over 3. And if I just activate this guy and grab the intersection, you'll see that it's listed as 4 pi over 3. 4 pi over 3 is exactly what you get if you take pi plus pi over 3. Pi over 3 and add pi. You get a common denominator and add them together, and you get 4 pi over 3. Now, of course, that's not the only other solution. Let's go ahead and record that while we're at it. Here, one solution is, now also, we have x equal, we did pi plus pi over 3, and that was equal to 4 pi over 3. Okay, let's go look again. If we want to keep going from this point up to the next point, well, it's exactly the distance that it takes for a tangent to repeat. And so that's a distance of pi again. This was 4 pi over 3, and we would want to add on another pi onto that to get this point here. I'll just activate that point. And you'll see that it's 7 pi over 3. Why is it 7 pi over 3? Let's go ahead and record it. This another x is, well, we had 4 pi over 3, and we were adding pi. Just to go through the steps so you can see it here, if we want to add these two together, the first one is a fraction, the second one is not, so we multiply the second one by 3 over 3. That gets us a common denominator. And this is going to get us 4 pi over 3 plus 3 pi over 3. And we can add them together now with the same denominator. 4 pi plus 3 pi is equal to 7 pi over 3. So we now have another solution, 7 pi over 3. We're going to have another solution if we add pi again onto this. So we're going to have x equal 7 pi over 3 plus pi. And when we combine these, once again, we get a common denominator, and it's going to look like this, 7 pi over 3 plus, and this one will be 3 pi over 3. And when we add those together, we're going to end up with 10 pi over 3 on the top. So far, we've found how many solutions? 1, 2, 3, 4 solutions to this thing. And that's not all of them. If you look at the graph, you will see that the solutions keep going and going. This one, the 10 pi over 3 was here. And then there's going to be another one, which is 13 pi over 3 here. And each of those we get just simply by adding pi onto the previous one. And those keep going off to the left. If we scroll to the left, you'll see that it just keeps going and going. There's lots of places where the purple, the tangent line, crosses the value radical 3. Okay, so we need somehow to capture the fact that we have not just the original solution here, but another solution here, and another one here, and another one here, and they keep going. And of course, we can't forget about going this direction. The original solution, which was where x was pi over 3, that was here. And if we want to go down to the solution below here, well, this is a distance of pi, but since we're moving to the left, we would take that pi over 3 and we would subtract we would subtract pi to get down to this point. And if we do the pi over 3 from here, pi over 3 is the x-coordinate. And if we subtract pi from pi over 3, that's pi over 3 minus pi, well, you have to do a little calculation there, common denominator, and you're going to see that you end up with negative 2 pi over 3. So there's another solution here, which is negative 2 pi over 3. And we can subtract pi again, and we'll get another one, negative 2 pi over 3 minus another pi. This is going to be negative 2 pi over 3 minus, if we get a common denominator, 3 pi over 3. And then minus 2 pi minus 3 pi gets us minus 5 pi over 3. You may see a pattern here. You may be able to guess what the next one is, but if you can't guess it, I can certainly tell you to calculate it like this, minus 5 pi over 3. If we want to move to the left one more step, we would just subtract pi from that, and that will give us another one. If we simplify this, it will come out to negative 8 pi over 3. That negative 8 pi over 3, if we want to see it on the graph, that's the one that is, I believe, right here. Oh, that was negative 5 pi over 3, and then the next one down is negative 8 pi over 3. And of course, we don't have to stop there. We can keep moving down, 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 and it will keep seeing places where angles, where the tangent of that angle is equal to that radical 3. Okay, so here's what we've got. In terms of angles x, where tangent of x equals pi over 3, we have a single one here, pi over 3. Then we have another one here, and another one here, and another one here, and they keep going to the right. And we also have another one to the left, and to the left, and to the left. They keep going to the left. And so how do we somehow capture all of this? The fact is, how many of these angles are there? There are infinitely many. And in the unit circle, those just correspond to going around the unit circle once or twice or 3 times or 4 times. Each one of those gives you a different angle, but brings you back to the same location of the unit circle, same value of tangent. Okay. So how do we put all of this together? Well, there's a formula that we use to do it, and it looks like this here. To solve tangent of x equal a number c. So this observation is going to work for any equation of the form tangent x equal a number. Just like ours, our number was radical 3. So the key is that first you have to find a single solution. The single solution we found by looking at the table, when our c was radical 3, the solution was pi over 3. That's the angle that has tangent radical 3. And then we somehow have to capture all of the other solutions, and here's how we do it. So what to look at in this observation, find a single solution, x equal inverse tangent of c. The reason it's written that way is if we can know from a table a value of an angle that has the correct tangent, tangent equal radical 3, I happen to know that x equal pi over 3 works, then we can just use pi over 3 here instead of this entire inverse tangent of c. But if we didn't know that and we needed to do it numerically or using a calculator, we would use the inverse tangent function to get a single value of c. And once we have a single value, that single value goes here. So what you see, tangent inverse of c, for us, that's going to be our pi over 3. And then it says plus n many copies of pi, where n is either 0, or plus or minus 1, or plus or minus 2, or plus or minus 3, and so on. Those of you who remember from the beginning of the semester, this is just a sort of long-winded way of writing n is an integer. And the integers, they're abbreviated with that big capital Z. But they just mean that n is in this set of numbers that goes ... minus 3, minus 2, minus 1, 0, 1, 2, 3, ... It keeps going in the positive direction and in the negative direction. N has got to be any of those numbers. And the idea behind the formula that I'm talking about is this one here, is that if you put your original single solution in here, so this is like one solution goes here, and then you can get more solutions by just picking a number for n, as long as it's an integer. That means n can be either 0, or any positive whole number, or any negative whole number, that is, any integer. And you plug in an integer times pi. So, for example, we could get a solution by taking our solution, pi over 3, plus any number n times pi, where n is an integer. And the idea behind writing it in this way is this gives you a sort of a formula for figuring out all of the different angles that solve this equation. To get all of the different angles, you would need to substitute in all of the different integers, all the different positive whole numbers, all the different negative whole numbers. Each one that you substitute in and replace in here will give you an expression that gives you another angle. That's a solution to this. So altogether, I'm just going to go back up and I'm going to put all of these pieces together. The solution to this problem, remember the original problem was tangent of x equals radical 3. And here's our final solution to this. Oops. We'll do it in black just to be consistent. So our final solution, the general solution, that is to say the solution that captures all of the possible answers, it looks like this. We take our one value, pi over 3, that was one answer that worked. And then we, then we add any number n, any integer, times pi. So these are our answers x. Here is our solution. And there's maybe just a little note here where n equals 0 or plus or minus 1 or plus or minus 2, etc. That's just a way of saying n is an integer. Okay, so here we have it. This is our solution. X is equal to pi over 3 plus n times pi. That's a way of somehow giving all of the different solutions, all the different values of x that make this equation true. This one right here. All right, that's it. In our next video, we'll look at basic equations involving cosine.